Good morning. I'm Rick Edgman. I'm your instructor for Management 602, Production and Operations Management. This is the 11th actual lecture in the course. We've had other days where you were using the time for, let's say, large assignments or for some other purpose. But today is the 11th actual lecture, and it is a continuation of a presentation that we started on quality tools and control charts. Fundamentally, it's just an introduction to quality tools and control charts. The first part of this material, we talked about things like the plan, do, study, act cycle, fishbone or cause and effect diagrams, Pareto diagrams, and perhaps a few other things. We introduced the notion of control charts. Today you'll see two examples of different types of control charts, and there are many different types. So I will tell you when we get the first new slide for today. This is just the cover slide for the entire set, which is labeled in your lectures, lectures 10 and 11. So if we focus today solely on control charts, then we had said last time that imagine that we're charting data, we're plotting data as you see that occurring from left to right on this chart. And what we're plotting could be just about anything. It could be that we are taking samples, and then each dot that is plotted represents the mean of a sample, and those samples are sequential. So first sample, second sample, third sample, each with n items included in the sample. So it could be the means, could be proportion of something, it could be the number of defects, it could be the standard deviation of the sample or the range of the data in the sample. So many options in terms of what could be plotted. We are going to look at only a few types of control charts that deal with just a few of selections from among those that I've just listed. But on each chart, imagine that we have the data itself and whatever lines that we want to add to the chart. So we're going to have the vertical and horizontal coordinates. The vertical coordinate will be the value of the thing that we are plotting. The horizontal coordinate will be the sequence, first sample, second sample, third sample, and so on. The 7 lines that we add, the ones that you see in this chart as green, yellow, and red, will be ones that are presented at the very center. The center is the average performance level of the thing you're plotting. That's why it says center line, and you see just as a generic symbol over on the left side of the chart, you see mu, the Greek letter mu, which you ordinarily associate with the mean. Well, it is the mean. It is the mean range, or the mean proportion, or the mean standard deviation, or the mean of whatever is being plotted. The other two green lines are the upper and lower 1 standard deviation lines, and those are positioned at 1 standard deviation of the plotted measure above and below, or more and less than the center line. The 2 yellow lines that you see are similar. They're positioned at 2 standard deviations, above for the upper 2 standard deviation warning line, and below for the lower 2 standard deviation warning line, or more and less of the measure that you're plotting. And then finally you see those red lines, and those red lines are positioned at 3 standard deviations distance from the center line, or from the mean. So generically, we are using the symbols mu and sigma over on the left side of the chart to represent the mean and the standard deviation of whatever plotted measure you're looking at. Now, in reality, it would be incredibly rare that we knew mu and sigma. So we will have to estimate those values from the data itself. Notice also on this chart, you see the letters A, B, C, and then you see beyond zone A, above and below the upper and lower control limits. So what do we have for those? We analyze the data itself by virtue of where it plots relative to these zones. Zone C are the areas of that chart between the mean or center line and plus and minus 1 standard deviation distance from that center line. Zone B are between the green and yellow lines. So between the upper 1 standard deviation line and the upper 2 standard deviation warning line. Between the lower 1 standard deviation line and the lower 2 standard deviation warning line. And then zone A is the data that would plot anywhere between 2 and 3 standard deviations away from the center line. So the one that you see near the upper right-hand corner of this chart would be data that would plot between the upper 2 standard deviation warning line, or the upper yellow line, and the upper control line, the upper red line. Similarly, you see the A down below. And the A down below is between 2 and 3 standard deviations away from the center line, just less than whatever that center line coordinate value is. So those are the zones on the chart, and we will analyze the data and how it's plotting and what it is trying to tell us by virtue of how it plots relative to those zones. So we described those 7 lines, just as we spoke about a moment ago, and then we talked about pattern analysis tests last time. And the pattern analysis tests are literally tests of or examinations of how the data plot relative to those zones we just talked about, A, B, C, and beyond A, both above and below the center line. We noted last time that there are 4 patterns that apply to absolutely any type of control chart. 4 patterns that are relevant for any type of control chart, including the 2 types of control charts that you will see today, one of which is called a C chart, another of which is called a P chart. So pattern 1. Before I describe pattern 1 again, we described it last time, let me just say that these patterns are patterns of unusual behavior if in fact there has been no change in the ordinary process behavior. Unusual behavior if there's been no change. So what do I mean by unusual behavior? I mean that, generally speaking, if there's been no change in the historic pattern of behavior of your process, that there's somewhere between about a 1 in 1,000 and a 1 in 250 chance, or at the lowest, a 1 in 100 chance, let's say, of seeing that particular pattern. It happens now and then. There's no viable explanation for it other than just, oh, well, it occasionally occurs. Somewhere between 1 in 100 and 1 in 1,000. On the other hand, if you see that pattern, it is almost certain that something has changed in the historic behavior of the process. It may even be because of something you intentionally introduced into the process. Something has changed, and there is a 99% chance to a 99.9% chance that that's what you're picking up on, is the change. There's only a 1 in 100 to 1 in 1,000 chance that there's no viable explanation. Only a 1 in 100 to only a 1 in 1,000 chance that there's no viable explanation, that things are performing as they historically have, you just happen to see the pattern. There's a 99% to 99.9% chance that in fact something has caused that pattern to emerge. And the pattern itself usually tells us a lot about the nature of what's happening. So pattern 1, we have 1 point plots beyond zone A on either side of the mean. Well, what does that mean? It means that you had a point that plotted at least 3 standard deviations away from the center line. So above the upper red line or below the lower red line, a single point. The fewer the points in the pattern, the more jarring the pattern is. The more that it's telling you, wow, something significant has happened, and it's happened quickly, abruptly. The more points that it takes, the more subtle the change. Hence, it took more data for you to pick up on the change. So pattern 1 usually represents a sudden and large change in the average performance level of whatever trait you're tracking on that chart, whether that be a mean, a standard deviation, a proportion, or something else. Pattern 2. Think about the center line, okay? The green line in the middle of the chart. So that's what we're talking about when we say here, 9 points in a row plotting on the same side of the mean. We're talking about, let's say, 9 consecutive points plotting above that center green line. Or 9 consecutive points plotting below that below the middle green line. Now that's a pretty long pattern, 9 points to uncover it. There is a chance of about 1 in 250 that pattern occurs, whereas the pattern 1, there's about a 1 in 400 chance that pattern occurs. Yet there's no viable explanation. There hasn't been any change in the historic performance of the process, you just pick up the pattern. Pattern 2, it's about a 1 in 250 chance, but pattern 2 usually represents a relatively small change in the average performance level of the trait that you are tracking. Relatively small, whether that's an increase, that is the 9 points plot above the center line, or whether that's a decrease in that plotted value, the 9 points plot below the center line. Pattern 3, you have 6 consecutive points that are either rising up, 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 or 6 consecutive points that are falling down, 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 down. Okay? No level performance, so nothing in that pattern that says up, 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 same, up, up. Okay, same isn't allowed for 2 consecutive points. It is strictly going up or strictly going down. That pattern even has a name. We call it a toolware pattern because so many of these tools, these charts, were developed for manufacturing processes back in the 1920s and shortly after. So a lot of times when that pattern was seen, it was seen as being indicative of something that was wearing out, okay, a tool wear pattern. But what it really represents, just more conceptually, is a persistent and ongoing change in the average performance level of whatever trait you're plotting on that chart. So an ongoing and persistent change in the mean, an ongoing and persistent change in the variation, an ongoing and persistent change in the proportion defective, whatever it is that you might be plotting or monitoring. Pattern 4 is a different type of pattern. So it's literally 1 point up, next point down, next point up, next point down, next point up, next point down, and so on. 14 consecutive points that alternate up and down. That usually arises from one of 2 sources. Okay. One source, which is very common, is that somebody has interfered with the process with good intentions, usually with good intentions, but that it's causing increased variation in the output. That is, they have inserted themselves unintentionally as an additional source of variation in what happens. So the first one was too small. Uh-oh, better adjust. Next one's too big. Uh-oh, better adjust. Next one's too small. Better adjust again. Next one's too big. Usually, if that's what's happening, what you see occurring in the data is not only is it going up and down, it's going up and down further and further and further as you proceed through the pattern, because the variation itself of the person who has inserted themselves. The other explanation that is very common for pattern 4 is that you think you have one process, but you have 2. And so the odd number points, 0.1, 0.3, 0.5, 0.7, and so on, those are coming from the first process. The even numbered points, 2, 4, 6, 8, 10, and so on, are coming from the second process. What do I mean by that? I mean, let's suppose that you have 2 machines that are supposed to produce identical output, but they're not. Okay, they're not. Instead, you need a separate chart for machine A and one for machine B, or for shift 1 and shift 2, or for person A and person B, and so on. So as much as you may want those processes to be identical, they're not, and at least the temporary remedy for that is that you have separate charts for each process. So those patterns are good for any type of control chart. They'll be the only ones that apply to the charts that you're going to see today. But there are 4 other patterns that are useful. And in particular, they are useful for what are called X-bar charts. So charts that literally plot the mean of continuous sorts of output. how much something weighs, or its volume, or its diameter, or things of that sort, how long something takes. So patterns 5 and pattern 6 are about changes in that average performance level. Patterns 7 and 8 will be about changes in variation. So pattern 5, note that it only takes 3 points. So that's going to be a pretty quick and a pretty large change in the average performance level. It says 2 out of 3 consecutive points plot in zone A or beyond, so they're at least 2 standard deviations away from the mean. So they're beyond, let's say, the upper yellow line, and either before or even after the upper red line. 2 out of 3 consecutive points in zone A or beyond. All 3 of the points on the same side of the center line. Okay, all 3 of the points, same side of the center line. So that could happen either above the center line, so in the upper half of the chart, or it could happen below the center line, lower half of the chart. But this is a rare pattern that normally indicates that you've had a fairly large, pretty abrupt, or sudden change in the average performance level of the process. Pattern 6 is similar. Excuse me, pattern 6, it's a little more subtle change, a little smaller change. That's why it took 5 points, not 3 or 2 or 1 or something like that to expose or to emerge. So 4 out of 5 consecutive points in zone B or beyond, all 5 of the points on the same side of the center line, or the mean. So you have at least 4 of the 5 points that are above the upper green line, and the remaining point is still above the center line. Or alternatively, that could happen on the lower half of the graph, so that you have 4 out of 5 consecutive points that are below the lower green line, but all 5 of the points on the same side of the center line. So all 5 on the lower half of the chart, say. That would be a relatively small, but a clear indication of a change in the average performance level of the thing that you're plotting. And then lastly, you have 2 patterns, patterns 7 and 8, that deal with changes in variation. One of them is a good pattern, the other one is a bad pattern, at least assuming that you haven't made calculation errors or something of that sort. So pattern 7, boy, that's a long pattern, 15 consecutive points. So long pattern, subtle, took a lot of evidence to convince you that there's a change. This says that you have 15 consecutive points that are plotting within 1 standard deviation of the mean. That is, they're within the center line, the green lines on the chart. They are all between minus and plus 1 standard deviation of the mean. That's usually a good pattern. That is almost always a good pattern. It's a pattern that indicates that you have been working on reducing the amount of variation that is in the process. And this pattern is a signal to you that your efforts have borne fruit. That you, whatever it is that you've done, you should now make permanent in your process so that you can reduce the amount of variation in what's occurring. Pattern 8 is the opposite. Pattern 8 is virtually always a pattern that we do not want to see. It's indicative not of a decrease in variation. Remember, variation is the enemy. We're not looking to produce variety. We're not talking about intentional variety. I want blue cars, green cars, red cars. We're talking about variation, that every green car should be the same color green coming off that production line. So when that is the case, what we don't want is an increase in variation. So this would be an indication of an increase in variation, that you have, out of 8 consecutive points, none of them are between the green lines. All of them are outside the green lines, some above the upper green line, some below the lower green line. That is virtually always an indication of a change, an increase in the amount of variation in the output. And then there were some questions that you could ask if you see any of these patterns. These are usual sorts of questions to try and uncover the cause of the pattern. So now let's talk about two specific types of charts, the C chart and the P chart. These rely on results from something that you covered in your statistics course. They rely on results from, not on using the formulas to calculate probabilities, but the results from or characteristics of the Poisson distribution, which we saw last week when we talked about queuing models, and the binomial distribution. The C chart makes use of results from the Poisson distribution. The P chart makes use of results from the binomial distribution. So the first one that we're going to look at is called a C chart. And we're looking at the C control chart for non-conformity. So what is a non-conformity? Imagine that I am looking at my cell phone. Okay, a non-conformity would be anything that was outside of the specifications that I have here. So for example, I might be looking at the number of scratches that are on the surface of the screen. There shouldn't be any scratches, but there might be some. Now, can I count the number of scratches? It would be easy for you to say yes, but you should give a qualified yes. And what I mean by that is, yes, I can count how many scratches there are if I can describe what it is that constitutes a scratch. Is it something of a particular length, minimum length, and a particular minimum depth? What is a scratch? So you need a so-called operational definition to refer to tell you what a scratch is and isn't. Is it something that can be seen from this close or from this far away? What is a scratch? So you need to know that. So sorry for the coughing, but the cold or whatever it is continues to hold on. So we're going to be looking at those. Those are based on the Poisson distribution. Poisson distribution looks at the number of occurrences of an event over a region of opportunity for occurrences. So for example, I might be looking at the enamel on a refrigerator. I have a refrigerator manufacturing line. And in that refrigerator manufacturing line, every refrigerator that comes off, maybe I look at it and I say, how many scratches are there in the enamel? I'd have to have an operational definition of a scratch, but I could look at that. Or I look at how many people are arriving in line over a 15-minute period. How many calls are coming through a switchboard, a telephone switchboard, over a 30-minute period or an hour period on Wednesdays, 8 to 9 in the morning on Wednesdays. So ordinarily speaking, that region of opportunity is defined relative to some amount of material or space or some amount of time or a particular time period. That's what region of opportunity is. And the idea is that we can count the number of occurrences of the event, but we cannot count the number of non-occurrences. So what does that mean by way of example? So one of the things that follow the Poisson distribution comes from the Napoleonic Wars. And in the Napoleonic Wars, Napoleon lost a lot of his cavalry because they were kicked in the head by their own horse or mule. So that was a large enough source of attrition for Napoleon that he needed to be able to model and predict how many of his cavalry could be expected to be lost due to that cause. So imagine the phenomena as an observer of somebody getting kicked in the head by a horse or a mule. Can you count how many times it happens if you're watching? Oh, I imagine you can. How about the number of non-kicks to the head? The number of non-occurrences of the event? Is it every time the horse kicks and misses? Is it every 10 seconds that goes by that somebody doesn't get kicked in the head? What is a non-kick to the head? The point is that any definition of the non-occurrence of the event would have an element of arbitrariness to it. So we can count the number of occurrences of the event over the region of opportunity for occurrence, but not the number of non-occurrences. And in theory, at least, you could have 0, 1, 2, 3,628,407 occurrences of the event. In practice, however, the number of occurrences of the event that you have, and this is similar to the discussion that we had last week when we talked about queuing models, it bunches up around whatever the average value is. Okay, so if the average is 3 occurrences of the event or 3.6 occurrences of the event, then you're going to have most of your probability around 1, 2, 3, 4, 5, 6, 7, 8, somewhere in there, and not much outside of there. So this will follow the Poisson distribution. So one of the things you need to know is that whenever something originates from the Poisson distribution, we can chart it using what's called a C-chart. We need to know the Poisson distribution, or at least we need to know 2 results from the Poisson distribution. We need to be able to estimate its mean, and then consider that chart that you saw with the coordinates for the 7 lines. The center line, the upper and lower 1 standard deviation lines, the upper and lower 2 standard deviation warning lines, the yellow ones, the upper and lower control limits, the red lines, which were positioned at 1, 2, and 3 standard deviations away from the center line, the mean. What that tells us is that if we're using a chart to model something that follows a Poisson distribution, that we need to know 2 things. And in truth, for the Poisson distribution, it comes down to 1 thing. We need to know the thing that plays the role of the mean, which we're going to symbolically represent by C. And we need to know the standard deviation. The standard deviation of the Poisson distribution, remember, is the square root of its mean. So we need to know C. We need to be able to take its square root. There's the mean, there's the standard deviation. With some caveats, the coordinates for those 7 lines on the chart would be C for the center line, which could be anything between 0 and infinity in theory. So a positive value is what I'm saying. And we need to be able to get its square root. And then the coordinates for those 7 lines would be center line, C, or our best estimate of C. And for the other 6 lines, C plus and minus 1, 2, and 3 times the square root. Now, when I said with a caveat, here's the caveat. The caveat is that the square root of C might be bigger than well, it's not going to be bigger than C unless C is less than 1. But the point is that by using those formulas, C minus square root of C for the lower 1 standard deviation line, C minus 2 times the square root of C for the lower 2 standard deviation warning line, and C minus 3 times the square root of C for the lower control line, it's possible that using those formulas would deliver a negative. Yet, you know that somebody can't be kicked in the head by a horse a negative number of times. I can't have a negative number of scratches on the surface of this mobile phone. So those are formulas, and the formulas are actually approximations. So what is it that we would have? We would have C plus or minus 1, 2, and 3 times the square root, recognizing that below the center line that 1 or more of the those lines that we're obtaining coordinates for might not be operative. That is, if the calculation delivers a negative result for the lower control limit, then simply speaking, you don't have a lower control limit, and you can't plot below zone A on the lower side. On the upper side, yes. Lower side, no. Similarly, that's going to happen, by the way, anytime that the value of C is less than 9. Anytime that the value of C is less than 4. You're not even going to have the lower 2 standard deviation warning limit. Anytime that the standard deviation is less than 1, you will not even have the lower 1 standard deviation line. Okay. Now, there's the formula for the Poisson probabilities. If you want to calculate those, you're not going to have to use that formula for a C-chart. You just need to know the results. But this says that to calculate the probability of any specific number of scratches, non-conformities, on the surface of this mobile phone, the probability of 3 scratches would be c cubed minus, or times e to the minus c divided by 3 factorial. For 5 scratches, c to the 5th times e to the minus c divided by 5 factorial, which would be what? 5 times 4 times 3 times 2 times 1 for 5 factorial. 0 factorial is 1. We've talked about that last week in terms of queuing theory. But we don't actually have to use this formula. Not here in control charts. We just need to be able to estimate the value of c, and hence to also get the square root of that estimate. That's going to be easy. And then we said, look, here you go. Here's sort of the results. The way that we're going to be able to estimate c is the following, that we're going to obtain some number of initial samples for most control charts, that is 20 to 25 samples of n items each. So 20 to 25 samples of n items in each sample. In this case, we usually say for this particular type of chart, 20 to 40 initial samples. The sample is always 1. It is 1 mobile phone with this much surface area. It is 1 horse over an hour. It is, etc. It is a refrigerator with X number of square feet of surface area that an ammo has been applied to. Right? In other words, the area of opportunity for occurrence of the event remains the same for each time that you sample. So m is equal to 20 to 40 initial samples of 1 each. So what we would do is we would simply get the number of occurrences of the event in the first sample, the number of occurrences of the event in the second sample, the third, the fourth, the fifth, let's say 25. Add those up and average them. And that would be my estimate of c for the Poisson distribution. And then I'd take the square root and then I have the estimated standard deviation. Once I've done that, that yields these formulas for the coordinates of the 7 lines, with the note for you that these lower lines, that you will not have a lower 1 standard deviation line anytime that c is less than 1. You will also not have a lower 2 standard deviation warning line anytime c is less than 2. And you will additionally not even have a lower control line anytime c is less than 9. Excuse me, I said 2. It's 1, 4, and 9. So anything less than 1 for c, excuse me, you will not have a lower 1 standard deviation line. Anything less than 4, you will also not have a lower 2 standard deviation warning line. And anything less than 9, you will not even have a lower control limit. So let's get an example for you just so that you can see how this works. Let's suppose that we have a scientific and technical materials company. And one of the things that they produce, they may produce a lot of things. One of the things that they produce would be gaskets for complicated scientific instruments. Now, you use gaskets every day, or at least they're present in your everyday life. As an example, the seal around the door on your microwave is a form of a gasket. Your car uses lots of gaskets. The seal on many windows or your door to your apartment, those are gaskets. But they're also used in complicated scientific materials. So for example, we talked about, I think previously at some time in this course, the O-ring on the Space Shuttle Challenger failing under the launch conditions that were prevalent when Challenger launched on that day in 1986. And when that happened, that O-ring, which is a gasket, was too brittle, it failed, Challenger blew up. So gaskets appear in your everyday life all the time. So we have this company. They produce complicated gasket material. Scars on that gasket material can be a problem. They can lead to failure. And what we're going to do is we are going to periodically take a sample of one piece of material. It doesn't even matter what size it is as long as it's always the same size. We're going to take a sample of a piece of material and we're going to count the number of, let's say, scars that are on that piece of gasket material. And we'll record that. And then later, we take another sample. We count the number of scars. We'll record that. Later, we take another sample, another piece of material, same size. Count the number of scars. Record that. Let's do that 25 times, or excuse me, 40 times. Excuse me. And the way that we're doing that is when I say periodically we're going to take a sample, it really means that every 25th time, every 25th piece of material, if you will, we're going to take that piece and we're going to examine it for scratches or for scars. So that's how we got our 40. We got a piece, 25 pieces later, we got another piece, 25 pieces later, we got another piece. And we did that for 40 initial pieces. Here's the data. Now notice that this is sequential, meaning this literally was the first piece we looked at. This literally was the second piece we looked at, the third piece we looked at, and so on, the 40th piece we looked at. The first piece had 4 scars. Now, of course, we would have to define what a scar was so that we could measure accurately, right? So we need an operational definition of a scar. We presume that that exists and that we've used it. First piece of material we examined, 4 scars. Second piece of material, 4 scars. Third piece of material, 2 scars, 3 scars, 1 scar, and so on. All the way out to the last 4 samples being 1, 5, 9, and 1 scars on the pieces of material. Now, I'm going to ask you to visually scan the data. And as you're going through, just try to answer the question, do you see anything that you think might be unusual? In other words, do you see any potential patterns that might exist here? Or does it look like the process is just moving along? Or do you see potential patterns? Now, I think most people, as they look through this, if they identify anything they think might be unusual, it turns out to be this 39th value, where you see 9 scars. Okay, the closest that you have to that, otherwise you had a couple samples with 5 scars. So a lot of people would say, well, you know, there might be something that happened out here. And if so, we'd want to know what it was that led to that, because scars are bad. Scars interfere with the ability of the gasket material to perform its intended function. Scars are bad. So we'd look at that. But, you know, it's one thing to say, well, I think that could be a problem, versus having some more rigorous standard or some more rigorous approach to tell you whether or not, in fact, it looks unusual. So here's one of the first things we'd do. We'd go ahead and estimate the mean. And if you were to add up those scars for those 40 pieces of material, you're going to find that those add up to 90. So there are 40 pieces of material, 90 total scars. That's an average of 2.25. There's C bar. There's the estimated mean. The estimated standard deviation is the square root of that, which turns out to be 1.5. Standard deviation equal 1.5. The upper control limit, no problem with the upper control limits. Upper control limits, anything above the center line, those are always going to exist for a C chart. So center line plus 3 standard deviations, 6.75 scars. Now, you know, I know, the whole world knows we can't have 6.75 scars. You could have 6, you could have 7, you could have 19, you could have 0. You can't have 6.75 scars. So anything that is above the center line is going to be what? 7 or more scars, which would tell you, by the way, that you are going to have pattern 1 point plots beyond zone A. Right? Because we had at that 39th sample, we had 9 scars or 9 scratches, whatever they were. So we are going to see pattern 1 here. Whether we see any other patterns, we don't know yet. Lower control limit, well, that is 2.25 C bar minus 3 times 1.5. That's a negative result for the calculation, so you do not have a lower control limit. Upper and lower 2 standard deviation warning lines. You can calculate those. Those are the results, 5.25 and negative 0.75. Therefore, you do not even have a lower 2 standard deviation warning line, not applicable. You do have a lower 1 standard deviation line. The calculation for which renders a value of 0.75, so that if you had 0 scratches on a piece of material or 0 scars, then you would have something that was below that lower green line in zone B, right? Between the lower green line and the lower yellow line. So that would be normally called zone B. You do have part of that zone B that is there. So if we were to plot the data, here it is, and I'm going to ask you to go through this and say, do I see pattern 1, pattern 2, pattern 3, pattern 4? Pattern 1, do I have a point that plots above the upper control line? Yes, I do. That's sample 39. What about pattern 2? Do I have 9 consecutive points that plot above the center line? Or 9 consecutive points that plot below the center line? 9 consecutive points above. There's 2, pattern broken. Then back above the center line, pattern broken. 1, 2, 3, 4 consecutive points below the center line. Broken here. You went back above. Below, 1, 2, 3, 4. But then you went back above. Below, above, above. Below, 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 below. You had 5 points. 6 points consecutively that were below the center line. 6 points. But it takes 9. Above, above, above. 3. Below, below, above, below, 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 above, below, 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 above, way above, below. Ordinarily what will happen is that if you even approach having a pattern that matters, one of patterns 1 through 4, this is a C chart, only patterns 1 through 4 apply. If you even approach one of those patterns being there, it will visually jump out at you. So this would have been very simple to say, no, we're nowhere close. Not on pattern 2, yes, pattern 1 was there. Pattern 3, what about 6 consecutive points that are falling? Or 6 consecutive points that are climbing? Do you see anything like that? 1, 2, 3, 4. Not 6. 1, 2, 3. Falling. Nowhere. These are level. They don't count. They break the pattern. As soon as you got falling, or excuse me, first point, second point, third point stayed the same. Broke the pattern. Same isn't allowed. Has to be strictly falling or strictly rising. Pattern 3, not there. Pattern 4. And I apologize for the coughing. I know that it's got to be distracting, but there's not a whole lot that I can do about it. So, pattern 4. Do you see 14 consecutive points that are up, then down, then up, then down, then up, then down? And the answer is clearly no. So, only pattern 1 is here. Those patterns are called out of control patterns. In other words, if you see one, it says that during that period where that pattern emerges, the process was out of control. Now, out of control can be good or bad. It depends entirely on context. In this case, I presume that we do not want scarred material. This was a bad indication. So, as we look at that, we would say something like this. Now, how did we calculate these? The coordinates for these lines? We calculated the coordinates for those lines, and this is called a control chart. We calculated the coordinates for those lines, including this point where the process was out of control. In other words, these coordinates are not, we're going to have to revise somehow. Now, we don't do that by being easier on the process, more lenient. We do that, in fact, by becoming more strict. And the way that we do that, there are two options that we have. One is we exclude the data from the period where the pattern was there. And if we have enough remaining data, we recalculate based on what remains. Alternatively, we could remove this 39th point. It's not that this point is unimportant. It is. We want to know what caused that pattern to emerge. We want to know why there were 9 scars at that point in time. Because if there was something that caused that, we want to fix it. But at the same time, this is non-representative of what the coordinates for the control line should be. So one of the things we could do is we could just remove this, and that would leave us with the other 39 points. Remove the 9 scars, so instead of 90, we have 81. And we could recalculate. C bar would be 81 scars, 39 pieces of material, whatever that is, about 2.05. The new standard deviation would be the square root of 2.05, about 1.41, I think. And then we would just, we would recalculate these and reinterpret, look for patterns. Another alternative would be remove this and then add a new point out here. Add a new, this would become the new 39th point, you'd have a new 40th point. That's an alternative as well. So you really have two options there for how you replace data where patterns happen to be before. But notice we're not giving the process a break. We're not being more lenient. In fact, what that would have done is it would have collapsed these a little bit. And it would have made it harder for the process to prove itself to be in control, not easier. So what's your interpretation? There you go. We saw pattern 1 at point number 39, and we would want to do something about that. We'd want to find out what it was that caused that. So we would take corrective measures. We would identify what the problem was. We'd take corrective measures. We would implement that. And then we would probably do one of two things. We would either, maybe we still haven't established control, so we need to get more data until we do establish that the process is under control, until there are no patterns in the data. But once we get there, I'm presuming that this company would want to drive down, to reduce, to drive down the average number of defects. So to do that, at some point, they're going to probably enter into Plan, Do, Study, Act. They're going to plan a change in the process that they believe will reduce the number of scars per piece of material. They would implement whatever change that was, so do it. They would study the results, probably using the control chart. Ongoing use of the control chart with the existing limits, or the limits to that point in time. Coordinates for those 7 lines to that point in time. Until one of the patterns emerged that told us that we were being successful. So let's see. What could tell you that you were successful if you continued to plot data after you made this change using the existing or the coordinates of the 7 lines to that point? Pattern 1. You don't have beyond zone A on the lower side, which would be less scars. You have above zone A on the upper side. That's more scars. That's bad. So not pattern 1. Pattern 2. What about pattern 2? Pattern 2 would be 9 consecutive points above the center line. That's not bad. That's not good. That's more scars. How about 9 consecutive points that were below the center line, below C bar? That'd be good. So pattern 2 might be a way to identify that your change has been effective. How about pattern 3? 6 consecutive points rising. Nope. That's increase in scars. 6 consecutive points declining. That would be a possibility for you. Of the process speaking to you to tell you that, oh, whatever it is, whatever change you made is working. So pattern 2, pattern 3 both have potential. Pattern 4, 14 points alternating, never has that potential. So that's what you would have as a possibility. Just a moment here. Okay, so that was the C chart, and remember that the C chart is based on the Poisson distribution. I'm going to show you one other type of control chart. It's called a P chart. And the P chart is based on the binomial distribution. So you're not going to have to use the binomial formula to calculate binomial probabilities. But we do need to know some results. Okay, we do need to know some results. Just like for the C chart, all we really needed to be able to do was to estimate the mean and the standard deviation, which was the square root of the mean. Similarly for the P chart, all we have to be able to do is estimate the mean and the standard deviation so that we can get the coordinates for the 7 lines against which we will plot the data. The name of the chart, ordinarily speaking, tells you what it is you're plotting. This is a P chart, so we are plotting some sort of a proportion. And oftentimes for this type of chart, it happens to be the proportion of defective items in a sample. So we're going to do the same sort of thing. We are going to need 20 to 25 preliminary samples. You can get more if you want. But it's generally considered that you need 20 to 25 preliminary or initial samples sequenced. You know which is the first sample, you know which is the second sample, the third, the fourth, the fifth, and so on. And each of those items, or samples rather, will have n items in it. So the 20 to 25, let's say you have 25 initial samples, 25 would be M. The letter M as in Marshall. Okay. So M. Number of samples, M. Number of items in each sample, N, as in Nancy. So we will have M samples of N items each. Now, here's the reality with this type of chart. The reality with this type of chart is that I could have a sample of 100 items in one sample and 75 items in the next sample and 60 in the next and 125 in the next. You could do that. There's nothing that prohibits that. But what it would do is it would end up producing a control chart where the 7 lines look like a city skyline with the height of the buildings going up and down. That's what would happen in 6 of your 7 lines. The only one that would remain constant would be your center line. But the others would look like city skyline. And so for that reason, people who actually use this type of chart, in theory, they could change the number of items in each sample, but in practice they don't. It's always the same value for n, whether that's 50 or 100 or 200 or whatever the case might be. Okay, so here's what you've got. What you have is that in each sample, you want to be able to estimate the proportion of items from the process that have some trait of interest. So maybe that trait of interest is that it's defective. Now, this is not obviously enough. This is not a plastic Coke bottle or a plastic beverage bottle. But you know that the typical plastic beverage bottle of a soft drink or a typical can, let's just say you get a can out of a vending machine. The typical can will have more than 200 things that they measure. Okay, for example, how round is it? What's the structural integrity? What's the crush strength on that? What about printing and labeling? There are so many things. Is it truly round or is it out of round? You know, so many things that they measure, about 200 traits, but in the end they render one decision. Either that can is defective or it's non-defective. So what you might do is say, look, this process is producing some proportion of defective cans. you are able to estimate what that proportion is with sample results. So your sample, let's say from this shift or this hour, get 100 cans. Okay? 3 of them are defective. So your estimated process proportion defective is p hat, as you see at the bottom of this slide, is equal to 3, the number of cans that were defective, divided by n, 100, the number of cans in the sample, 3 over 100, 0.03. Now recognize that is your best estimate for the proportion defective during the period from which the sample came. But it is only an estimate. Only an estimate. So what is a better estimate? Maybe if you observe the process over a longer period of time, periodically sampling from it, so that you have a bunch of different estimates, and then maybe you can combine that estimate. Well, that's what we're going to do. So we're going to sample m preliminary samples of n each. M preliminary samples of n each. The first sample will have this many items with the trait of interest, let's suppose defective. Second sample, this many items with the trait of interest, and so on. So your overall estimate, or better estimate, combined estimate of the proportion of items from the process with the trait of interest, suppose defective, would be the total number of defectives divided by the total number of items. Now, this formula works whether you're using the same number of items in each sample or if you're varying that. That doesn't matter. It's still the total number of defectives divided by the total number of items that were sampled. But if you just had the same number of items that you sampled every time, you could just average the p hats. The p hat from the first sample to the second sample and so on, the mth sample, divided by the number of those p hats that you have, m of those. And we'd call that p bar. So this is your standard deviation, your mean. This is the standard deviation of p, the estimated value of p. I should say S of p hat, or S of p bar rather. Square root of p bar times 1 minus p bar over n. So again, remember n is the number of items in a sample, and you can see why if you changed n from sample to sample to sample, that this value would go up and down. This radical would go up and down in terms of its value. Therefore, most people will just keep the same sample size every time. But then here are the coordinates for the 7 lines on the chart. P bar, plus and minus 1, 2, and 3 of those standard deviations. Note that these formulas really are approximations. What that means is that this is a proportion. That proportion has to be between 0 and 1. Assuming you don't make any calculation errors, any result that you get on the upper side that was more than 1, you made a mistake. Or you just don't have that upper control line, let's say. Similarly, proportion has to be between 0 and 1. If I got a negative result for any of these and I didn't make a mistake, then I just don't have that line. So when might you not have an upper, one or more of these upper lines? Well, if p bar is really close to 1, that would be what would lead to that. Similarly, when would you not have any of these lower lines, or some of these lower lines, 1 or more of them? If p bar was really, really small, closer to 0, okay, then that's a possibility. So let's just get you an example of this. So let's suppose that I have a company, they produce wallpaper or designs for walls. Custom wallpapers, custom borders that you might be using in your house or in your place of business. So we have that. Here you go. Maybe this is a custom border right here, about a 9-inch border or something like that, that goes around at some level on your wall all the way around your room, or maybe all around to line the ceiling in your room. So something like that. So we have South of the Borders as a company that produces these wallpaper and wallpaper borders. But you know what? Not everything they produce is perfect. And because not everything they produce is perfect, that means that they're going to want to monitor the process so that they can see when that process is not delivering the sorts of results it needs to deliver or that it's expected to deliver. So here's what we do. We will take a sample each day for 25 consecutive days to try and establish the control chart and its coordinates. So 25 consecutive production days, Monday through Friday, let's say Monday through Friday, Monday through Friday, Monday through Friday for 5 weeks. 25 consecutive days, 100 rolls of wallpaper border each day that we sample. And we have criteria that we would be applying to tell us whether or not that wallpaper border is defective or non-defective that they sample. So each of the rolls is inspected to see whether or not it's defective or not defective. Okay, and we would have operational definition of defective. This is a P-chart, patterns 1 through 4 apply. It is a P-chart because for every item that you look at, either it has the trait of interest or it doesn't. Presumably, whatever happens on one item doesn't influence what happens on another item. You're sampling a set number of items and you are counting the number and eventually the proportion of items that have the trait of interest in your sample. So this is a binomial distribution. I would suggest go back to your statistics and say, what are the characteristics of a binomial? P-chart. That'll lead you to a P-chart. What are the characteristics of a Poisson? That would lead you to a C-chart. So here you go. Here's the data. Day 1, 100 rolls were sampled. 13 of those were defective. Day 2, 100 rolls were sampled. 4 were defective. And so on and so forth out to day 25. 100 sampled. 10 were defective. Now, if I looked at this, I'd say, okay, what's the proportion defective? Well, gee, I have lots of estimates running around. I have one from each day for 25 days. 13 out of 100, 0.13, 4 out of 100, 0.04, 7 out of 100, 0.07, and so on. Or I could get a combined estimate. I could add those up. And if I add those up and divide by the total number of rolls, then I'd have 13 plus 4 plus 7 plus 11 and so on and so forth, plus 3 plus 10, divided by 2,500. What is that? 2,500 rolls. 196 of which are defective. That would lead you to a p-bar of 0.0784. So there is the center line on your p-chart, p-bar. We need to know the standard deviation because you need to know both the mean and the standard deviation to be able to get the coordinates for the 7 lines on the chart. Standard deviation is the square root of p-bar times 1 minus p-bar divided by n, where n is the number of items in each sample. P-bar was roughly 0.08. 1 minus p-bar roughly 0.92. And we had 100 items in each sample, so 0.0784 times 0.9216 divided by 100, square root of that. That is 0.02688. Now, what I will tell you real quickly is that what is the coordinate for the lower control line? Well, according to the formula, it's going to be p-bar minus 3 of these. And I don't know exactly what that is, but I can tell you this, that the calculation itself would go slightly negative. You are not going to have a lower control limit on this chart. You will have the coordinates for the other lines, but you won't have a lower control limit. So here are the calculations for those 7 lines, and you can see them. P-bar, 0.0784 for the center line. P-bar plus 3 times the square root that we calculated. 0.159 for the upper control limit, and so on. No lower control limit. No lower control limit. So what we can do, however, is get the coordinates for the other lines. So notice that for you to have something above the upper control limit, you know, what are the possible values in your sample? 0 over 100, 1 over 100, 2 over 100, 3 over 100, 99 over 100, 100 over 100. The actual possible values that you're going to be plotting of p hat from one sample to the next sample to the next sample are going to only be things that are possible in increments of 1/100th, 0, 0.01, 0.02, 0.047. This says that it's going to take at least 16 defective rolls, which would deliver a value of 0.16 to plot above the upper control limit. Did you have that in any of your data? 14. So you're not going to have pattern 1. Nothing plots above that upper control limit. What about the other patterns? Pattern 2. Pattern 2 is 9 consecutive points above the center line. Well, to be above the center line, functionally the only possible values, like I said, are 0, 0, 1, 0, 2, 0, 3. So it would take 8 or more defectives to plot above the center line. Do we have any place where that happens 9 consecutive times? 13? Nope. Less, less, more, 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 less, more, more, less, 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 more. More, more, less, less, more, 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 less, less, more, less, more. No pattern 2. Pattern 3, do you see 6 consecutive points that are falling? Anywhere? Not a chance. 6 consecutive points rising? Anywhere? Not a chance. Don't have pattern 3. Pattern 4, up, down, up, down, up, down, up, down, up, down. Up, down, up, up, down, up, down, up, up. Nope, you're just not going to have that. So there will be none of the patterns that appear on this chart. None of the patterns appear. Notice, by the way, on this chart where it says that the -3 standard deviation line is 0, it isn't. We don't have a lower standard deviation, lower control limit. It's just that the smallest possible value is 0. But in point of fact, we don't have a lower control limit. So if I were to look at this, I would say, okay, the process is in control. What does that mean? It means that the process is performing stably, that there are no patterns. It doesn't necessarily mean that I'm happy with the average performance level. So if I'm not happy with that average performance level, then I would probably do something like the following. I would probably look at this and say, well, process is in control. Let me go into plan, do, study, act out here. And when I go into plan, do, study, act out here, obviously the sort of change I'm looking for is a change that I think will drive down the defect rate. So I would identify a change, or my team would identify a change that we think will drive down the proportion of defective rolls of wallpaper. Would implement the change maybe on a small scale because it might not be as effective as we need. It might require a big investment in new equipment or something like that, so that we've really got to get our payback to make it worth doing. Who knows? So I would plan a change. I'd do it probably on a small scale. I'd study the results, which means I would continue to plot the data using these same coordinates for the lines. Plan, do, study, until I saw definitive evidence of change in the process. Preferably change for the better. Preferably reduce defect rate. So what patterns might tell us that? Pattern 1, point plots beyond zone A, either side of the center line. Well, we don't have a lower control limit, so we don't have a lower zone A. That would have been great if we had something down there, but we don't. So we're not going to get that. How about a point above, beyond zone A, up here? Well, that's bad. That's not going to tell us that we were effective in what we were doing. That'd be an increased defect rate. Pattern 2, How about 9 consecutive points above the center line? No, that would be an increased defect rate. Pattern 2, 9 consecutive points below the center line. Yeah, that could be good. Pattern 3, 6 consecutive points rising. No, that's an ongoing increase in defect rate. Pattern 3, 6 consecutive points falling. That could be good. So both pattern 2 and pattern 3 have potential. Pattern 4 is never something that tells you whether or not you're improving or not. Okay, so pattern 2 or pattern 3 both have potential for speaking to you on behalf of the process that whatever change you implemented is driving down your defect rate. Now, if I got that signal at some point, then I would recalculate my new control limits under the new change process once I implemented the change on a broader scale. And I'd establish what the new lines were. And I would continue to monitor the output from the process. If I got to a point where I said, I'm still not, I'm glad we made improvement, but I'm still not happy enough with the defect rate. It's still too high for my taste. Our profit margin is being cut because of that. Then once I had control over the new process established, I would move into plan, do, study, act again. And I would, over time, cascade down that defect rate to get something lower. So that's pretty much what you've got here. So that first point here on interpretation, there's no patterns that are in your chart. The fact that there are no patterns tells you that it's in control. Doesn't mean that you like the level at which it's in control, but it is in control. That's a good thing. It means it's stable. It means you can work on the process. But it doesn't mean that it's in control at a level that you're happy with. And that's what the second point means. It does mean, however, that we could go ahead and engage in plan, do, study, act for the purpose of process improvement. So control charts are often used just to monitor, ongoing monitoring of a process. But they can also be used, as we've just been talking about, as a continuous improvement tool. And that is the more contemporary use of this. So you've seen two types of control charts, the C chart and the P chart. There are a lot of others. I think I may have mentioned last time that I developed some very specialized charts that were used at the Johnson Space Center, so by NASA, and also by the National Institutes of Health and so on. Did that more than 30 years ago. And they're useful charts for a limited set of circumstances. Okay, but the two charts that you saw today, the C chart, the P chart, those apply all over the place, as do a few other charts that we're not taking a look at in this course. Those other ones would have been these types of charts, X bar chart, R chart, S chart. We're just not going to see that in this class. So if you want to see a few other videos that could be useful at some point in time, whenever we move into Six Sigma, some of these might be useful for you. These are lectures that I delivered at a 500-year-old university in Sweden in 2016. I used to be affiliated with that university and spent 20% of my time there for about a 3-year period. So I still have a lot of friends and so on. A lot of my former students are at that university, which is why it is I had that affiliation. But some of these might be of value to you, especially when we talk a little bit about Six Sigma, which would be everything from the cursor down. So next we'll move into another topic, but that is the end of this topic right here. So see you next time.